What if the Milky Way is not just a place where life happens, but a kind of life in its own right? It's a strange question, almost impolite to ask. Galaxies are grand collections of stars and gas, not beating hearts. They drift, collide, and spin for billions of years, minds nowhere in sight. And yet, the longer we look at the Milky Way, the more it behaves like something that keeps itself going. It doesn't burn all its fuel at once. It regulates, recycles, organizes. If you were very patient, cosmically patient, you might watch it inhale and exhale gas in slow motion, pulse energy through its veins, and carve long-lived patterns into its rotating disk, as if writing a message to the future version of itself. So, here's our provocation. Set aside carbon chemistry and warm ponds, love and language, and all the fragile miracles of biology. Ask a simpler question. Can a thing be alive if it shows the hallmarks of life? Self-maintenance, energy flow, information, growth, even if none of its parts are cells. To make that question useful, we need a lens. Biologists often describe life with a few sturdy ideas. Homeostasis, staying within bounds, keeping internal conditions in a life-sustaining range. Metabolism, turning matter and energy into work, structure, and repair. Information and structure, preserving patterns, memories, instructions, so the thing doesn't dissolve into chaos. Growth and reproduction, changing over time, and in some sense, giving rise to more of the same. These aren't the only definitions of life, but they're good handles. They let us look at a creature or a candidate and ask, does it do these things? And if it does, how? With what machinery? What consequences? Now look up. Our galaxy is a spiral some 100,000 light-years across, with a barred center, curled arms, and a haze of dark halo around it like a cloak. In the middle, a quiet monster, a supermassive black hole, the mass of 4 million suns, not currently feeding but capable of lashing out with energy that can change the galaxy's weather. Across the disk, giant clouds of hydrogen, stirred by gravity, magnetism, and shock waves from exploding stars. On those shock fronts, newborn stars light up like campfires along the arms, burn their fuel, and die in brilliant storms that seed the next generation with heavy elements. Above and below the disk, fountains and bubbles of hot gas, as if the galaxy were breathing. None of this is mystical. It's physics, but it's also a pattern. A long, resilient conversation between gravity trying to clump things together and feedback pushing back so the clumping doesn't run away. That push and pull sets a tempo. The Milky Way doesn't explode into one catastrophic starburst. It also doesn't freeze into quiescence. It modulates. It keeps itself in a narrow band where new stars can still form, where the gas isn't all locked up or blown away. That looks suspiciously like homeostasis. Then there's metabolism. The galaxy swallows pristine gas trickling in from the dark halo, and the cosmic web processes it through the disk into stars, then exhales some of it richer now with carbon, oxygen, iron back into the halo where it cools and falls again. Material cycles, energy flows. The galaxy runs on gradients, hot to cold, high pressure to low, dense to diffuse. That's what all metabolisms do. They exploit differences to build and maintain structure in a universe that otherwise prefers to even out. If you could speed up time, you'd watch the Milky Way metabolize matter into pattern. But metabolism without memory is a bonfire, spectacular, brief, and forgetful. Does the galaxy keep information? It does. Not in genes, but in orbits and chemistry. Spiral arms and a central bar carve lane lines for gas. Resonances shepherd stars into streams and rings. The disk stores a fossil record in metal gradients, like growth rings in a tree. Older stars are poorer in heavy elements, younger ones richer, and where you find them tells you where the galaxy has fed itself. And when it rearranged its bones, even the motion of stars, swarms tilting or rippling through the disk, remembers encounters with satellite galaxies, as if the Milky Way's skeleton still aches from old collisions. Information, written into motion and composition, lets the galaxy persist as a recognizable self across deep time. What about growth and reproduction? Here, the metaphor stretches. Galaxies don't lay eggs, but they do grow and transform. They merge, swallowing smaller companions, mixing and healing into a new whole. They spawn star clusters, and on rare tidal nights, little dwarf galaxies pulled from stretched ribbons of gas. More subtly, a galaxy like ours seeds thousands of planetary systems with the elements of life. It isn't reproducing its galactic body, but it is sowing the possibility of biospheres, scattering a billion experiments in being. If you widen the camera and wait long enough, maybe that's a sort of reproduction, not copies, but descendants' worlds that echo their parents' chemistry and dynamics. Still, there are objections, good ones. The Milky Way isn't an organism with a skin. It leaks. Material flows in and out. Bound is a fuzzy word at galactic scales. There's no intention here, no plan, no will to live. The feedback that regulates star formation is not a nervous system making choices. It's a network of physical processes settling into a steady state. Call that life, and you risk turning life into a metaphor so broad it says nothing. And yet, life on Earth is also a network of physical processes, settling for a while into stable patterns. Single cells are leaky. Ecosystems don't have a single mind. Forests maintain climate zones beneath their canopy, pump water, share nutrients through fungal threads, and keep their community within ranges where it can continue. Are forests alive, or are they ecosystems inside which individual life flourishes? We accept both at once because it helps us understand the whole. So perhaps the safer claim is this: the Milky Way is an ecosystem writ cosmic, a self-maintaining, far from equilibrium system that regulates, metabolizes, records, and grows. Calling it alive doesn't prove it has desires. It simply focuses our attention on the patterns that let it persist. The thermostats and feedback loops, the rivers of gas and cosmic rays, the bar and spiral that steer traffic, the black hole's occasional heartbeat that resets the weather. The language of life gives us a map for the galaxy's behavior. Why reach for that language at all? Because it changes what we think we're part of. If the galaxy is a dead backdrop, then life is a weird local glitch that temporarily sparks and then goes out. If the galaxy is a self-maintaining engine that reliably manufactures heavy elements and hospitable real estate, then life, our kind of chemical curiosity, becomes a late-stage product of the galaxy's long metabolism. You and I, the cameras behind our eyes, might be the galaxy's way of noticing what it's been doing all along. That idea is both humbling and electric. It turns the night sky from a cold audience of stars into the slow choreography of a system that makes and remakes itself. And it raises a sharp, unnerving question. If a galaxy can look so lifelike without being alive, where do we draw the border? At cells? At genes? At consciousness? Or do we admit that life is not a cliff but a slope, a progression of self-maintaining worlds, from cells to forests to planets to maybe galaxies. To find out, we'll test the Milky Way against those 4 criteria, one by one. We'll ask how a disk of gas and stars can hold itself in balance. We'll watch matter flow through it, like blood. We'll read the memories it keeps in its structure. We'll trace how it grows. And what, if anything, it leaves behind. Along the way, we'll keep a skeptic in the room, pointing out where the metaphor fails. And at the end, we'll step back and ask the only question that really matters. What does it mean for us? Because if the Milky Way is, in some meaningful way, alive, then so are we twice over. First, as animals in biospheres on a small wet world, and second, as temporary thoughts inside a larger living pattern we barely understand. Riding a spiral arm through the dark, trying to name what we belong to, if a living thing keeps itself within life-friendly bounds. On Earth, homeostasis means your body holds its temperature steady despite weather, exercise, or a mouthful of ice water. In a galaxy, the pressures are different, but the principle is the same. Despite 1,000 forces trying to run away with the system, gravity collapsing gas into catastrophic starbursts, stellar explosions blasting that gas into emptiness, the Milky Way tends to settle into a narrow, surprisingly steady band of behavior. It neither burns all its fuel at once nor stalls out forever. It cruises. That balance is hard-won. Gravity loves to overdo it. If a cold cloud of hydrogen in the Milky Way's disk gets dense enough, gravity squeezes it tighter, which makes it denser, which makes gravity stronger. Still a feedback loop that, left unchecked, would turn vast regions of the galaxy into stars in a single reckless binge. But the moment new stars ignite, they push back, they shine, they blow, they stir. The cloud that might have collapsed into one more stellar neighborhood gets shredded, pressurized, heated, and sometimes lofted high above the disk, like breath on a cold window. Collapse begets heat. Heat slows collapse. The loop closes. The galaxy's thermostat ticks. What are the moving parts of that thermostat? Imagine a whole constellation of regulators, each acting on a different time scale and length scale, all layered together. 1. Young stars as local fire breaks. Newborn massive stars flood their surroundings with radiation and charged particles. Their light pushes on dust grains. Their ultraviolet photons strip electrons from atoms, and their winds plow shells through the gas. The very act of starbirth produces a neighborhood that's suddenly hostile to more starbirth, at least in that immediate patch. It's as if every campfire builds a ring of damp dirt around itself. 2. Supernovae as citywide alarms. A few million years later, the biggest of those newborns detonate. A supernova doesn't just end a star's life. It writes a memo to the whole interstellar medium. Shockwaves drive turbulence, random motion that puffs gas up and keeps it from collapsing too quickly. And they heat large volumes into a hot, low-density phase. The galaxy's disk becomes a layered soup. Cold, star-forming clouds immersed in warmer gas, all threaded with pockets of million-degree bubbles that leak upward like steam from a kettle. That multi-phase mixture is not an accident. It's an equilibrium born of constant shove and countershove. 3. Magnetic fields and cosmic rays as invisible scaffolding. Invisible doesn't mean unimportant. Magnetic fields snake through the disk and halo, quietly adding pressure, an extra don't collapse term in the galaxy's physics. Cosmic rays, high-energy particles accelerated by supernova shocks, slip along those magnetic highways, spreading energy far from where it was injected. They can help launch winds, carry heat, and sustain the puffiness of gas over scales much larger than any single star-forming region. Think of them as a circulatory system that redistributes pressure and energy, where gravity would prefer everything to fall straight down. 4. Rotation and shear as traffic laws. Because the disk rotates, different rings move at different speeds. That shear stretches clouds, tears some apart, and feeds others along spiral lanes, where shocks are strong enough to pile gas up into star-forming knots. Rotation keeps the disk from collapsing straight inward. Spiral patterns and the central bar behave like traffic circles and on-ramps, organizing the flow so that gas doesn't just crash into the center and ignite all at once. The result is a regulated supply line to star factories rather than a single giant blaze. 5. The halo and black hole as climate control. Above and below the disk, the Milky Way's hot halo, its circumgalactic medium, acts as a giant heat sink and reservoir. When the disk overproduces energy, supernova-driven winds and chimneys vent some of that excess into the halo. When the disk underproduces, cool filaments of gas drip back down. On even larger scales and longer cycles, our central black hole, usually quiet, can inject energy in episodic outbursts that inflate colossal lobes of hot plasma over the galaxy's poles. Those events don't happen often. But when they do, they reset conditions across a vast volume, the way a rare forest fire can reshape an entire valley's ecosystem for centuries. Taken together, these processes compose a negative feedback network. If star formation runs hot, feedback strengthens and pushes it down. If it runs cold, gas cools and settles until stars form again. The system prefers an in-between state, not perfect, not static, but persistent. You can watch this in slow motion through two simple ideas: thresholds and timescales. Thresholds. Gas only collapses into stars when certain conditions are met. It must be cold enough, dense enough, and shielded enough from radiation to let molecules form and temperatures drop. In a stable Milky Way patch, turbulence and magnetic support keep most gas hovering near, but not past those thresholds. Every so often, a spiral arm squeeze, a cloud-cloud collision, or a cooling fluctuation nudges a region over the line. It forms stars, then promptly kicks itself back below the line with heat and pressure. Like a thermostat set to 21 degrees Celsius that allows a degree or two of wiggle, the galaxy bounces around a self-chosen set point. Time scales. The Milky Way's feedback loops are staggered. Radiation pressure and ionizing light act immediately. Supernovae act after a few million years. Cosmic rays and hot bubbles propagate for tens of millions. Fountains cycle over tens to hundreds of millions, and black hole outbursts punctuate the story every few million to tens of millions of years when fuel happens to gather near the center. Because the responses arrive at different speeds, the system dampens its own swings. A brief surge of star formation triggers quick breaks, radiation, winds, followed by medium breaks, supernovae, turbulence, and then slow breaks, outflows, and halo heating. Even if the first response doesn't fully quell the surge, the later ones often will. You don't need fine control when you have many layers of coarse control. One way astronomers know the Milky Way self-regulates is that its star formation efficiency is stubbornly low and remarkably uniform. If you measure how much gas sits in the disk and how fast new stars appear, you find the galaxy is converting only a few % of its raw fuel into stars per cloud lifetime. Not because the gas can't collapse, it can, but because the minute it starts to feed back, puffs it back up. The same story plays out in countless spiral galaxies. More gas means more star formation. Yes, but not in a runaway way. The relation curves gently, like a well-behaved thermostat that turns the furnace up a little when the house gets cold, not full blast. The Milky Way has ways of nudging itself back. Suppose gas accumulates unusually in one arm segment. Stars ignite in a burst. Radiation scours the surrounding cloud. Supernovae soon lace the region with turbulence. A superbubble fractures the disk and vents hot plasma into the lower halo. The local gas surface density drops, the region goes quiet, and in the halo above it, a plume of enriched material begins to cool, fall, and eventually rain back into the disk, often not where it started. What looked like a local boom becomes, over tens of millions of years, a galactic-scale redistribution, a breath out, then in, or suppose the opposite. The disk enters a lull. Gas has been stirred too vigorously. Clouds can't find enough calm, shielded pockets to collapse. But turbulence decays. Hot gas radiates away its energy. Warm gas cools to cold. Magnetic fields relax into different configurations. Inflowing filaments from the halo keep adding mass. The thresholds are crossed again. A new round of stars lights up. The quiet ends. Even the geometry of the Milky Way supports self-regulation. A rotating disk has a natural stability criterion. If the combined support from rotation, turbulence, and pressure is too weak, the disk fragments. Too strong, and it becomes sterile. Observations suggest many star-forming disks hover near the borderline, right where gravity can create clouds efficiently. But feedback keeps those clouds from swallowing the neighborhood. Near the edge is not an accident. It's where the system gets the most stars per unit of misery. Crucially, self-regulation does not mean sameness. The set point can drift with the galaxy's age and structure. During the Milky Way's youthful years, when gas was more plentiful and infall from the cosmic web more vigorous, the thermostat likely allowed a warmer, busier house. Thicker disks, higher turbulence, more frequent outflows. As time went on and the fuel trickled in more slowly, the same feedback mechanisms maintained order at a quieter level. Structural changes like the growth of the central bar or the thickening of the bulge reorganized traffic patterns, moving where and how stars form without eliminating the overall balance. In other words, the galaxy's climate changed, but its climate control kept working. And like all good ecosystems, the Milky Way's homeostasis includes edge cases that appear to break the rules but instead prove them. Starbursts are the galaxy's fevers, when a system is triggered by a merger, a strong inflow, or a violent bar instability. Gas piles into the central regions so fast that the usual brakes can't keep up. For tens to hundreds of millions of years, star formation roars at 10 or 100 times the normal rate. But fevers break. The enormous feedback from countless supernovae and perhaps an awakened central black hole vents the core, heats the halo, and starves the center of fuel. Afterward, the galaxy often returns to a calmer state, sometimes transformed by the ordeal but again regulated. The thermostat wasn't absent, it was overwhelmed. Then it caught up. At the other extreme, tiny dwarf galaxies can be too easily bullied by feedback. A single burst of supernovae can blow out much of their gas, pushing them into long, quiescent stretches. Their thermostat is twitchy, overcorrecting in gusts. By contrast, a massive spiral like the Milky Way has enough gravity to keep most of its gas bound and enough moving parts to avoid catastrophic overreactions. Size, in other words, helps homeostasis. there's more room to redistribute energy and mass without losing the system. Then there's morphological quenching, a fancy way of saying the galaxy's own shape can cool its star factories without cooling its gas. As the central bulge grows, or as the bar becomes more dominant, the added gravitational structure increases shear and stabilizes the disk against fragmentation. The raw material can be present, but the disk resists breaking into star-forming clouds. It's like piling books on a trampoline. Same fabric, fewer bounces. Sometimes the set point shifts because the frame of the system stiffens. One of the most poetic expressions of galactic homeostasis is the galactic fountain. Supernovae and stellar winds punch holes in the disk and launch plumes of gas into the lower halo. Up there, far from the star-forming commotion, the gas cools, mixes with the surrounding medium, and eventually drifts back down, often displaced by hundreds or thousands of light years. In the process, metals forged in stars get stirred into the broader environment, and fresh, partially cooled material is delivered to regions that need it. The fountain is both a relief valve and a delivery truck. It diffuses the local pain of star formation and resupplies the disk in a way that smooths out extreme highs and lows. Layer cosmic rays on top of that, and you get a self-regulating wind. The more intense the star formation, the more cosmic rays are produced. The more cosmic rays, the stronger the pressure gradient, pushing gas out of the disk along magnetic field lines. Those winds carry away not just mass, but also angular momentum and energy, push star formation higher, and the wind strengthens, which reduces the gas supply and cools the frenzy, turns star formation lower, and the wind weakens, allowing gas to pool. The system contains its own throttle. What about the central black hole, that quiet monster sitting in our core? For most of the Milky Way's recent life, it's been dozing. But evidence suggests that even a quiet, supermassive black hole can flicker awake and burp energy into its surroundings in occasional episodes. When that happens, huge lobes of hot gas bloom above and below the disk, like the galaxy exhaling from its lungs. Those events don't happen often. But when they do, they can suppress new star formation over large regions by keeping gas too warm and too buoyant to settle. In a body, hormones drift slowly through the bloodstream to adjust appetite or stress. In a galaxy, a black hole's outburst is a hormone spike, brief, powerful, and felt everywhere. Of course, all of this would be academic if the galaxy were a closed pantry. It isn't. The Milky Way lives with the door open to the cosmic web. Streams of low-density gas thread in along filaments, drip through the halo, and replenish the disk. Without that inflow, the galaxy's carefully tuned thermostat would gradually run out of material to regulate. With it, the system can maintain a steady conversion of gas into stars for billions of years. Not a bonfire, but a hearth. The inflow rate, the wind strength, the feedback efficiency, the disk's stability, together they define a moving balance. When one changes, the others tend to respond. Astronomers sometimes summarize this intricate dance with a deceptively simple phrase: self-regulation of star formation. It's a technical way of saying the Milky Way behaves like a creature that knows not to gorge and not to starve. Push on it here, and it adjusts there. Heat a patch, and pressure rises to prevent collapse. Let a patch cool, and gravity quietly resumes its work. The miracle is not that any one process is smart. It isn't. The miracle is that the network of dumb processes produces a smart outcome. Steadiness. There's a philosophical tingle in that. Homeostasis is one of the things we intuitively recognize as lifelike, not because of what it is, but because of what it protects. Continuity. A living thing, not just a cell, but a forest, a reef, a planet's climate, spends most of its energy defending its own conditions for being. The Milky Way, without intention or plan, seems to do the same. Not perfectly, not always, but enough that, across billions of years, it holds itself in the Goldilocks zone for making stars, planets, and eventually the strange observers asking whether it's alive. Call it what you like. Thermostat, equilibrium, feedback, resilience. By any name, the Milky Way's homeostasis is the quiet background music under everything else we'll talk about. Without it, there would be no slow, reliable production of heavy elements. Without it, there would be no long eras of stable starlight for planets to orbit. Without it, life like ours, patient, cumulative, subtle, would be far rarer. In the end, alive or not, the galaxy acts like something that wants to continue, and that, more than any formal definition, is the heartbeat of homeostasis. If homeostasis is how the Milky Way stays within bounds, metabolism is what it does there, taking in raw material, transforming it, moving it around, and sending the wastes and byproducts back out in ways that make the next round possible. It's not digestion in a literal stomach, but it is a chain of flows, mass, momentum, heat, light, magnetic stress, cosmic rays cycling from the outskirts to the core and back out again, like breath and blood. Let's start far from home, in the dark. The cosmic web. Our galaxy sits at a junction of invisible filaments, made mostly of dark matter, laced with thin gas. Over billions of years, that gas drifts toward the Milky Way's gravity well, pooling into a warm, hot halo, the circumgalactic medium, or CGM, that extends hundreds of thousands of light years in every direction. Think of the halo as the galaxy's atmosphere and pantry combined. A reservoir that exchanges with the disk below. It's tenuous and hot, but not static. Parcels of it cool, condense into wisps and filaments, and begin a long fall inward. This is how fresh fuel arrives. Without it, the Milky Way would have burned through its star-forming gas long ago and gone silent. With it, the frontier keeps supplying the interior. Crossing the last tens of thousands of light years, the infalling gas passes through wind and weather. Outflows from the disk drum against it. Magnetic fields thread it. Cosmic rays seep into it. Some of that gas mixes with material previously launched out of the galaxy. By the time it reaches the disk, it's no longer pristine. It's seasoned. In metabolism, what you ingest becomes you only after blending with what you were. Galaxies are no different. Now we enter the interstellar medium, the ISM, the Milky Way's true working fluid. It isn't one thing. It's a mosaic of phases. Cold, neutral hydrogen at tens of degrees above absolute zero. Warmer atomic gas at thousands of degrees. Warm ionized layers draped around bright stars, and scattered hot bubbles, 1,000,000 degrees or more, carved by ancient supernovae. The ISM is not a neat layer cake. It's foam and filigree. Shock fronts, magnetic strands, and shearing flows constantly tangle it. Energy cascades from large structures to small eddies and back again. That turbulence matters. It supports the gas against collapse. It also crumples it into dense knots where collapse can begin. The same brush that paints clouds also erases them. Within the densest, darkest folds where dust grains block starlight and cooling can run to completion, hydrogen atoms settle into molecules. On the surfaces of those dust grains, chemistry blooms. Two hydrogens meet, bond, and drift off as H2. Carbon and oxygen find each other to form CO and a zoo of other molecules. Dust is the galaxy's catalytic scaffold, the equivalent of enzymes, lowering the barriers so reactions and cooling happen at the right pace. Without dust, molecular clouds would struggle to form and survive. Without molecules, gas would not become cold and heavy enough to shatter into cores. In these shaded depths, the galaxy's metabolism focuses. Raw inflow turns into stock. Gravity now takes the stage, gathering those molecular knots tighter until they cross thresholds where collapse is inevitable. Inside, densities climb, temperatures rise, and at last, nuclear fusion flickers on. Stars ignite. In terms of bookkeeping, this is the moment the Milky Way converts gas into long-lived, energy-releasing structures. If you want to track the currency of galactic metabolism, track the power turned into starlight. For the next billions of years, those stars will repay the galaxy's investment, radiating heat into the abyss. But the galaxy's most consequential chemistry happens not in the quiet middle-aged years of small suns, but in the boisterous youth and sudden deaths of the massive ones, and in the slow, steady exhalations of evolved giants. Newborn heavyweights blast stellar winds that sculpt their birth clouds, mixing fresh elements into the surrounding medium. When the biggest die, supernovae hurl iron and a spray of other metals across light years, seeding their neighborhoods with the ingredients for planets and life. Lower mass stars later enter red giant phases and AGB winds, puffing away carbon dust, silicates, and S-process elements. The ISM grows richer, grain by grain. In a biological metabolism, we'd call this anabolism, building up complex molecules from simple ones. A galaxy does it by forging new atoms and locking them into dust and gas that will feed the next generation. All of this comes with energy accounts that must balance. A single supernova releases enough energy to heat and stir enormous volumes of gas. A constellation of them carves superbubbles that merge, percolate, and sometimes punch through the disk entirely, opening chimneys to the halo. Along magnetic field lines, cosmic rays, charged particles accelerated in those blasts stream outward, exerting a long arm of pressure that can help push gas up and away. Radiation pressure on dust lends another shove. The combined effect is to loft material into the halo in plumes and sheets. This is the galactic fountain, matter rising from the disk, cooling, mixing, and later raining back down, often far from where it launched. It's both waste removal and resource redistribution. It prevents any single region from hoarding all the metals, and it refills regions that have run lean. Notice the rhythm. Inflow from the cosmic web, and cooled halo trickles in. Clouds gather, stars form, feedback stirs and vents. Enriched gas climbs, cools, and returns. That's a cycle, not a line. On. Earth, water cycles through evaporation. Clouds, rain, rivers, and sea. In the Milky Way, baryons, ordinary matter, cycle through halo, disk, star, and halo again. Each lap leaves the system slightly changed. The gas grows more metal-rich. The dust-to-gas ratio rises. The typical cooling times shorten. Clouds can form faster. Planets can build easier. A metabolism is not just flow. It's flow that biases the next flow. Some of the material doesn't come back quickly. In regions of intense star formation, winds can accelerate gas to escape velocity, especially in the galaxy's outskirts, where gravity's grip is weaker. Those outflows enrich intergalactic space, sharing metals with the void. Call it shedding weight or perspiration. The details are poetic, but the point is real. To maintain its structure, the Milky Way must export entropy. Stars turn gravitational and nuclear energy into light. That light streams away into the cold. Hot gas carries heat to the halo and beyond, where it can dissipate. Outflows carry off excess momentum and metals that would otherwise choke star formation. Life and galaxies are both dissipative structures. They keep their own order by accelerating the universe's march to disorder elsewhere. Energy, then, is the master key. Follow it, and you follow the galaxy's metabolism. Gravitational potential energy is released as gas falls into clouds. It stirs turbulence, which partly cascades to small scales as heat, partly radiates away, partly banks in magnetic fields. Nuclear energy in stars emerges as photons from gamma rays at the core to ultraviolet and visible at the surface, and as winds of particles. Supernovae convert a fraction into shocks, heat, and cosmic rays, which in turn do work on gas far away. Along the way, radiative cooling is the quiet accountant. Atoms excited by collisions emit photons, shedding energy so gas can condense again. Without cooling, the cycle would jam. Without heating, it would collapse. Metabolism lives in there between. Transport matters too. Energy must get from where it's injected to where it can regulate. Magnetic fields provide rails. Alfvén waves, ripples in magnetized plasma, can carry energy across large distances. Cosmic rays move at near light speed, diffusing or streaming along field lines, subtly pushing on gas everywhere they go. Even starlight, absorbed by dust and re-emitted in the infrared, exerts a pressure that, in dense regions, can launch gas off the disk. These are the galaxy's vascular systems, not tubes, but pathways that give the metabolism reach. What about the central black hole, the compact, silent thing in the core? Most days it's a background character in our galaxy, sipping rather than feasting. But even intermittent episodes when gas manages to fall into its grasp can unleash outsized feedback. Jets or winds that heat and displace vast amounts of gas above and below the plane. Those events are rare in a quiet spiral like ours. But when they happen, they can alter the entire halo's thermodynamics for millions of years, like a sudden hormonal pulse that changes appetite and sleep across the whole body. Afterward, the disk's metabolism resets at a slightly different baseline. Zoom down again from the grand to the granular, the molecular cloud. Inside a cloud, star formation is a predator. It eats the conditions that allow it to exist. As soon as a cluster turns on, its radiation and winds erode the parent gas. This is self-limiting metabolism, but it's not just destruction. The erosion exposes new surfaces. It compresses some pockets while dispersing others. It seeds the local region with heat and ionized gas that can catalyze further chemistry once the shock passes. What looks like a death sentence from one angle is a kind of digestion from another. The cloud is being broken down and reassembled into stars, planets in the making, and enriched medium fuel for the next clouds. Even planets, though tiny by galactic standards, feed back into this budget. Dust coagulates into pebbles, then planetesimals, then worlds. Some of that solid material is locked away for billions of years, sequestering metals that otherwise would be free to cool gas. Disks around young stars launch disk winds that carry small grains back into the ISM. Giant planets migrating through disks can fling leftover debris back into space. Over immense times, the sum of countless planetary systems slightly changes how metals are partitioned between dust and gas, tuning cooling rates, cloud lifetimes, and star formation thresholds. It's a small lever on a huge machine, but it points to a truth. In metabolism, downstream structure feeds back upstream. Metabolism isn't just about matter, it's about information in motion. not memory, which we'll explore later, but instructions that ride on the flows. Spiral arms and the central bar are pattern generators. As gas orbits, it encounters those moving waves, is compressed, forms stars, and is released. The bar torques gas, transporting angular momentum outward and mass inward. That inward drift can feed central star formation or, occasionally, the black hole. Outward transport lets the outer disk expand or maintain its rotation curve. In a living cell, enzymes and gradients guide molecules to the right places at the right times. In a galaxy, gravitational patterns do that work. The result is not uniform cooking, but regulated kitchens, rings, lanes, and resonances where transformation is more likely. We should talk about timescales, because metabolism is tempo as much as flow. Gas can cool from warm to cold in a few million years if it's dense and metal-rich. Molecular clouds live for 10 to 20 million before feedback shreds them. Star clusters form over a few million, then disperse their lower mass members into the field over hundreds of millions. Fountain cycles up and down can take tens to hundreds of millions. Halo accretion waxes and wanes on giga-year scales. Black hole outbursts, when they happen, leave imprints that linger for millions. These nested tempos are what let the Milky Way metabolize continuously without synchronizing into boom and bust everywhere at once. When one part runs hot, others are cooling. When one region exhales, another inhales. The sum is steadiness. If metabolism builds the galaxy, it also ages it. Every cycle leaves behind stars that won't return to gas for a long time, if ever. The average metallicity of the ISM rises with each generation, changing how gas cools. Metals radiate more efficiently, so enriched gas collapses into clouds more easily. But dust and radiation pressure also alter how feedback couples, sometimes making outflows more effective. The balance shifts. Old spirals often thicken. Bars grow, bulges fatten, and the disk's shape and shear suppress some kinds of cloud formation while encouraging others. Aging metabolism isn't failure. It's transition, the moving target that homeostasis tracks. Is there waste in galactic metabolism? Yes, and it is useful. Outflows carry away not only heat, but also excess angular momentum and low-density gas that would otherwise dilute star-forming regions. Hot halos, initially energized by star formation and occasional black hole episodes, act as buffers that can store energy and matter, then release them when cooling winds. Even the diffuse radiation field starlight scattered by dust does work by heating the lowest density gas just enough to keep it from sinking into every small gravitational nook. Waste streams prevent clogs. They keep the cycle from poisoning itself. A good metabolism is also local. The Milky Way does not process matter evenly. Spiral arm segments flare bright, with H2 regions bubbles of ionized gas around OB stars, while inter-arm regions go quiet. The central few thousand light-years have their own drama, with dense gas lanes along the bar and a star-forming ring near resonances. The outer disk, poorer in metals and lower in pressure, forms stars more sparsely, its clouds more fragile. This patchwork is not disorder, it's division of labor. Different niches metabolize at different speeds. The whole is steadier because the parts are diverse, and sometimes metabolism falters. A major merger can deliver so much gas to the inner galaxy that outflows can't vent it fast enough. The result is a starburst, a fever that temporarily reroutes every flow toward rapid conversion of gas into stars. Feedback then overshoots, creating a wind that scours the center, heats the halo, and damps star formation for a long while after. The system learns, in a sense. The next few 100 million years run cooler. On smaller scales, a massive star-forming complex can blow out its own chimney, quenching starbirth locally for tens of millions of years, while neighboring regions continue as usual. Resilience is not never failing, it's failing without collapse. Why call all of this metabolism rather than mere physics? Because the metaphor highlights function. The flows aren't random. They maintain the galaxy's ability to keep making stars at a sustainable pace, to distribute enrichment, to avoid both runaway collapse and sterile dispersion. They amplify the patterns that preserve the system. If the Milky Way's matter simply fell to the center and stayed, the story would end in a quick blaze. If energy injections simply blew everything away, no story would happen at all. The real galaxy sits in the narrow, moving channel where inflow, processing, and outflow cooperate. Look again at the requirements for life: intake, transformation, waste, repair, growth. The Milky Way takes in gas from the halo and cosmic web, transforms it into stars, planets, and heavy elements, vents energy and matter in outflows that cool and return, repairs its star-forming ability by recycling and mixing, and grows not just in stellar mass, but in complexity. The ISM today is richer and more chemically intricate than it was 7 billion years ago. Its dust grains carry ices and organics. Its clouds feature long carbon chains and precursors to prebiotic molecules. None of this guarantees biology, but it stacks the deck. If metabolism is the art of turning gradients into structure and structure back into gradients, the Milky Way is a master. There's one more layer to the analogy that's easy to miss: purpose without intent. A living metabolism has goals: survive, reproduce, because evolution carved them. A galaxy has no genes, no selection, no nervous system whispering continue. And yet the flows act as if continuation were the aim, because only those configurations persist. A galaxy that failed to vent would choke. A galaxy that failed to cool would starve. A galaxy that failed to mix would splinter into isolated fates. The Milky Way is the survivor we see, because its metabolism kept it in the basin where long-lived spirals live. Not because it chose to, because the physics of feedback and flow weeded out the alternatives. In that sense, calling this a metabolism isn't to pretend the Milky Way is an organism. It's to remind ourselves that function emerges. Put gravity, gas, radiation, magnetic fields, and time together in the right proportions, and you get a machine that harvests energy from its surroundings and constantly reinvests it in keeping the machine running. That's the heart of metabolism. That's the work our galaxy quietly does while we sleep under its light. And us? We are downstream of these flows. The iron in our blood and the calcium in our bones rode a supernova's shock. The water in our cells condensed in molecular clouds, shielded by dust made in red giant winds. The warmth that lets us think at all comes from a star ignited by a century of local collapses and local breaks, at the end of a long thread of inflow from the halo. We are metabolized products and, in some infinitesimal way, participants. Every radio transmission, every fusion reactor we one day build, every rocket we send into the halo will write a small human signature onto the Milky Way's flows. We're latecomers to a kitchen that's been cooking for 10 billion years, but we are finally awake in it. So yes, the Milky Way processes and recycles matter and energy. It eats and breathes in its fashion, not with mouths and lungs, but with infall and fountains, cooling and feedback, turbulence and transport. It shapes raw inflow into stars and worlds, and it escorts waste into a halo that remembers, mixes, and returns it. That is a metabolism, and it is very much alive. Homeostasis keeps a system steady and metabolism moves matter through it. But without memory, even a well-regulated galaxy would smear into noise. Life persists by storing instructions. A galaxy preserves patterns instead. It writes continuity into orbits, chemistry, and shape, so the Milky Way can remain itself while everything inside changes. Think of structure as the galaxy's memory. A long, evolving script that tells gas where to flow, where stars ignite, and how byproducts return. That script is not conscious, yet it is stubborn. It carries the imprint of ancient jolts, and it copies those imprints forward by guiding the next round of flows. To ask whether the galaxy is alive, we must ask how well it remembers anything. Begin with orbits, the simplest carriers of memory. From above, stars circle the center like cars on a multi-lane highway, yet none follows a perfect circle. Each oscillates gently in and out, up and down, tracing epicycles around a guiding path. Those motions encode birth conditions and subsequent nudges. A star born in a cold, quiet cloud begins nearly circular. One jostled by giant clouds, spiral shocks, or a passing dwarf galaxy rides a wider, hotter loop, bobbing higher above the plane. Orbit shapes are portable archives that move with their owners, preserving clues about turbulence at formation and about every gravitational shove since. Add enough orbits together and patterns emerge, the way ripples reveal the stone that started them. Forward. Motion families amplify the message. In velocity space, nearby stars cluster into moving groups, sharing similar speeds and directions because they felt the same shove. Data reveal wave-like spirals when you plot vertical position against vertical speed, evidence of the disk still ringing from a past encounter. There are ripples in rotation rates across the sun's neighborhood, and streams gliding through like schools of fish. None of these features would exist if the disk were perfectly relaxed. They are afterimages, preserved by inertia and refreshed by recurring patterns. A single nudge fades, but the bar and the arms, like slow tides, keep restating the signal. Motion, then, is a palimpsest. Old writing visible under the new, guiding fresh strokes. To understand how memory is organized, consider the galaxy's gravitational potential, the invisible landscape that channels everything. From above, the Milky Way shows a central bar and several spiral arms unwinding from its ends. These are not fixed objects but waves, overdense ridges slowly rotating through the disk. Gas entering a ridge is shocked, compressed, forms stars, and then drifts ahead, leaving newborn clusters as glittering punctuation. Because the pattern rotates at its own speed, each parcel experiences the wave as a periodic instruction. The bar adds stronger, straighter lanes that funnel gas toward the center, while the arms braid material outward. Together, they are the operating system, writing rules that persist longer than individual clouds or clusters. Across cycles, resonances make the script bite. At special radii, a star's natural oscillations match the pattern's speed, so tiny shoves add coherently. There, stars trade angular momentum with the bar or arms, sliding inward or outward without heating their orbits much. This gentle relocation is radial migration. It subtly mixes the disk while leaving it ordered, moving metal-rich stars outward and metal-poor stars inward over billions of years. Gas also responds. It piles into resonant rings that sparkle with young clusters, and it avoids zones where orbits clash. Because resonances are tied to the pattern, Their signatures endure. Even as individual arms wax and fade, the machinery for reorganizing traffic persists, copying organization into every new generation of material. The central bar deserves special emphasis because it lasts. Bars arise when rotating disks redistribute angular momentum. Once established, a bar can survive for billions of years, slowly evolving as it exchanges torque with stars, gas, and the surrounding halo. It channels gas along straight dust lanes into an inner ring, feeding bursts of star formation and occasionally. In doing so, it builds a denser center that paradoxically keeps the bar stable. Thus, the pattern helps preserve itself, a feedback between structure and flow. Where the bar meets the arms, traffic circles form, shocks sharpen, clouds crowd, and clusters bloom. Even if spirals come and go, the bar's backbone keeps the disk's large-scale memory coherent. Chemistry is the other great archive. Every star locks the composition of its birth cloud into its outer layers, where temperatures are low enough that elements remain. Ratios of oxygen, magnesium, silicon, carbon, and iron become a birth certificate. Because different kinds of supernovae enrich gas on different clocks, those ratios also act as timers. Massive stars explode quickly, adding alpha elements. White dwarf detonations arrive later, adding iron. Measure both, and you estimate age. Measure totals, and you infer birthplace, since the inner disk has seen more star formation and is richer in heavy elements. This practice, called chemical tagging, lets astronomers group dispersed siblings and reconstruct star-forming neighborhoods long after gravity has scattered them across the sky. Chemistry across the disk forms a gradient that memory can read. Inward regions, long busy, reach higher metallicity. The outskirts lag, but radial migration smears the line because stars wander far from their cradles. At any radius, you find a spread in iron, alpha elements, and ages, evidence of mixing by patterns rather than random heat. Another chemical signature divides the disk into two intertwined components. The thick disk, older and puffier, carries elevated alpha at given iron, a fossil of turbulent youth when star formation was fierce. The thin disk, cooler and younger, shows lower alpha at similar iron, marking calmer times. The overlap tells a story of transition, a galaxy settling, yet keeping the records of its adolescence. Beyond chemistry, shape records pressure from outside and inside. Star-forming rings often sit near resonances where traffic piles up, glowing signposts tied to the bar's pattern speed. Straight dust lanes along the bar betray shocks that steer gas inward. Farther out, the disk warps, one side tipped up, the other down, likely torqued by the halo and by orbiting companions. A warp is not efficient. It persists because the forces that twist the outskirts keep working. Across the disk ride bending and breathing modes, vertical waves excited by a passing satellite. They crest and trough over hundreds of millions of years, slowly damping. While they last, they modulate cloud formation, quietly shaping where new generations will light the night. In the stellar halo, memory is even clearer. There, you can trace long, cold streams, ribbons of stars torn from dwarf galaxies and clusters as tides unspool them along their orbits. Each stream is a sentence about mass and motion, written in the alphabet of energy and angular momentum. Read many sentences, and you uncover chapters, major mergers that delivered large fractions of the halo in a single event. Some debris dives through the disk on elongated tracks, stirring waves with each passage. Some wraps around the outskirts, phasing into nearly polar loops. Because the halo's stars rarely collide, these signatures remain sharp for billions of years, a fossil record preserved in kinematics, chemistry, and the geometry of the sky. All of this rests on a scaffold we cannot see. Dark matter. It supplies most of the galaxy's mass and fixes the overall gravitational well. The halo's shape influences which orbital families are stable, how the bar slows, and where resonances land. A rounder halo lets simple orbits persist. A more elongated halo couples strongly to the bar, redistributing angular momentum more efficiently. Even the disk's thickness and its warp's precession carry hints about the unseen distribution, though dark matter is invisible. Its fingerprints cover everything. It sets the tempo on which visible memory can write, and it guards that writing by damping extreme responses. In effect, the potential is the paper. Stars and gas are the ink and binder. Memory must also be copied forward. Spiral structure begets more spiral structure because the mass concentrations it creates support the very waves that created them. The bar drives gas inward, building a central mass concentration that, paradoxically, helps the bar endure. Chemical enrichment lowers cooling times, seeding efficient cloud formation, and changing how feedback couples to gas. Even the circumgalactic medium remembers. Outflows lace it with metals and heat that alter where future inflow condenses and how easily it falls. The next accretion arrives informed by yesterday's behavior. Patterns are not photographs, they are attractors. Preferred states the system rediscovers after disturbances. Copying is imperfect, but bias is persistent. And persistence is what memory ultimately needs to stay itself tomorrow. Every archive fights noise. For the Milky Way, noise is turbulence from supernovae, random kicks from giant clouds, slight chaos where patterns overlap, and erratic arrivals of small companions. Some orbits remain regular, others wander. Some chemical signatures link siblings, others blur into the crowd. Some streams stay razor-sharp, others dissolve. Yet noise also mixes, and mixing prevents brittleness. It spreads elements so that planets can form across wide swaths of disk, not just in a few privileged locales. It softens gradients that would otherwise trap gas and stall renewal. The galaxy's balanced forgetting helps preserve what matters. Rotational support, organized traffic, inside out, enrichment, and a stable, star-making climate overall. You can read the archive because motion, chemistry, and shape are complementary. Measure 1,000 local stars, and you can reconstruct rotation, thickness, waves that crossed. And the pace of enrichment, the sun likely migrated outward a little over time, carried by resonances that rearranged neighbors without heating them. Our neighborhood's chemistry, rich in oxygen and iron, reflects long, steady processing rather than wild bursts. Calm kinematics tell of a thin disk layered upon an older, thicker one. At larger scales, the halo's streams outline ancient cannibalism. The bar records a long habit of torque, and the warp displays continuing dialogue with the environment. Structure is compressed knowledge, a living index that links yesterday's pushes to tomorrow's possibilities for stars like ours. Why does any of this belong in a discussion about life? Because persistence requires memory. A cell repairs its membranes. A forest maintains its canopy. Earth's climate stabilizes water and air. The Milky Way, too, preserves and propagates the patterns that maintain it. Bars and arms regulate traffic. Gradients keep cooling efficient. Enrichment copies instructions forward. Scars of perturbations guide new behavior. The halo remembers outflows and returns them mixed. None of this thinks. All of it continues. That is the heart of lifelike behavior. Flows that recall themselves. We live inside that continuity. Our world is a sentence in the galaxy's long book, written in orbits and elements, revising itself slowly, but always in conversation with what came before. Metaphors are powerful tools, but they can also bend reality until it snaps. Calling the Milky Way alive draws our attention to regulation, recycling, and memory. But it risks blurring the very boundaries that make life distinct. This section puts the brakes on our romance with the idea and asks, bluntly, where does the analogy fail? What isn't lifelike about a galaxy? And if the metaphor misleads, how do we talk about the Milky Way's order and persistence without borrowing the language of biology? 1. The boundary problem. No membrane, no self. Living systems are bounded. A cell's membrane is not just a bag. It's a selective, actively maintained interface that distinguishes inside from outside and regulates flows with exquisite specificity. The Milky Way has no such skin. Gas and stars exchange with the circumgalactic medium. Satellites pass through. Tides with the local group tug on the outskirts. You can draw a radius around the disk, but that line has no transport proteins, no pumps, no receptors. The galaxy is porous by nature and by necessity. Without an actively maintained boundary, it's hard to argue for a discrete self, in the biological sense, more ecosystem than organism. 2. No genotype, no high-fidelity inheritance. Life is not only bounded, it is coded. DNA, or RNA, stores information with redundancy and error correction, enabling high-fidelity replication and cumulative selection. The Milky Way has structure, but no genome. Spiral arms and a bar are not instructions. They are transient solutions of gravity and rotation. The galaxy cannot copy itself with inheritance of specific traits. When galaxies merge, the outcome depends on mass ratios, orbits, gas content, not on a coded blueprint. Without a genotype and an information system that is copied into offspring, the word reproduction loses its strict meaning and becomes a poetic way to talk about pattern persistence. 3. Evolution by natural selection versus physical settling. Biological evolution produces design-like features without a designer. By selecting among heritable variations, galaxies evolve too, but mostly by dynamics. Dissipation, mixing, and gradual structural changes driven by gravity, feedback, and environment. There is no population of Milky Way, clones competing with inheritable differences. Instead, galaxies slide toward attractor states, determined by their mass and history. Bars arise because certain mass distributions make them likely. Rings appear where resonances accumulate traffic. That's compelling physics, but it isn't Darwinian evolution shaping adaptations across generations. It's settling into stable patterns. 4. Teleology trap. Regulation without goals. When we describe galactic feedback as a thermostat, it's easy to smuggle in purpose, as if the system wanted to avoid starburst or quiescence. But the brakes and accelerators in a galaxy don't intend anything. They are side effects of local rules: radiation pressure on dust, supernova heating, magnetic tension, cosmic ray pressure whose net effect often dampens extremes. Life's feedback networks exist because past organisms with better regulation left more descendants. Galactic feedback exists because the laws of physics link cause and effect in predictable ways. The stability that results is descriptive, not normative. There is no ought to keep the star formation rate in range, only a tendency to do so under broad conditions. Homeostasis, but of what and how tightly? A mammal holds body temperature within a degree. A forest maintains humidity and soil chemistry over seasons. The Milky Way's set point is looser and drifting. Its star formation rate has risen and fallen by factors. Its structural parameters, bar strength, pattern speed, disk thickness, evolve. Gas fractions decline as fuel is used and cosmological infall wanes. That's not a failure, it's expected, but it means galactic homeostasis is coarse and contingent, a statistical steadiness rather than tight regulation. Living homeostasis uses sensors, signals, and actuators. Galaxies have feedback, yes, but no dedicated control architecture. Stability is emergent, not commanded. Metabolism. Without metabolism, we've argued that the Milky Way processes inflow into stars and outflow, exporting entropy like any dissipative structure. Yet biological metabolism is a chemically gated network of enzymes, cycles, and energy currencies. ATP, proton gradients, operating in a narrow temperature and pH range with repair pathways when parts break. Galactic processing has no comparable chemical specificity or repair machinery. Clouds form and disperse. Stars ignite and die. Nothing repairs the bar or replaces a broken spiral segment because it was damaged. Patterns re-emerge because the conditions favor them, not because an internal plan directs maintenance. 7. Reproduction. Reconsidered. Yes, tidal dwarfs can condense in tails during interactions. Yes, clusters form in bursts. Yes, biospheres may emerge on planets. But none of these are offspring that inherit the Milky Way's traits with fidelity. Tidal dwarfs lack the parent's dark matter halo. They form in special circumstances external to routine disk dynamics. Star clusters are subsystems, spin-off products without the architecture of a galaxy. Biospheres, while romantic to consider descendants, are the result of local planetary histories, not a replicated galactic program. The metaphor of reproduction stretches so far here that its scientific bite dulls. 8. Information versus memory versus meaning. We showed that orbits and abundances store information about history, but life's information is functional. Genes are instructions that build the very machinery that reads and copies them. Galactic information is descriptive, not prescriptive. Metallicity gradients don't instruct gas to collapse. They change cooling rates, which change probabilities. Orbital resonances don't command migration. They allow it. That matters. Without a code that specifies its own reproduction and repair, a system can be richly patterned and still not be alive in any rigorous sense. 9. Entropy and the arrow of time. Living systems locally decrease internal entropy by spending free energy, exporting disorder to the environment. A galaxy is also a far from equilibrium system, but its organizing principle, gravity, tends to increase clumpiness, while the overall thermodynamic entropy of the universe soars. Stars burning nuclear fuel increase entropy enormously. Black holes swallowing gas do the same. The Milky Way's structure is compatible with rising entropy, but it is not a low-entropy island fighting constant decay with precise molecular work. The resemblance to metabolism is suggestive, not strict. 10. Scale and agency. The mind's eye misleads. We perceive agency in rhythms, arms that seem to shepherd, a black hole that breathes, fountains that exhale. But those words compress timescales of millions of years into a heartbeat and attribute will to flows that follow gradients. A storm hunts warm water. A wildfire consumes a forest. We've learned to keep those as metaphors. Galaxies deserve the same caution. Agency requires sensing, modeling, and acting toward goals. A spiral pattern is powerful, but it senses nothing. It is a standing wave in a rotating medium. 11. Category errors. Dunes, flames, hurricanes. Sand dunes migrate, maintain shape, and even reproduce by calving smaller dunes. Flames propagate, feed on fuel, and respond to changing conditions. Hurricanes regulate their internal structures by exchanging heat, mixing air, and adjusting angular momentum. They even die when environmental support collapses. None are alive. They are self-organized flows that persist while gradients last. Galaxies belong in this company. Breathtakingly complex, deeply structured, yet still physical patterns rather than organisms. If we call them alive, where do we stop? At storms? At convection cells in a pot of soup? 12. Anthropic bias. We live in a survivor. The Milky Way's balanced behavior might tempt us to ascribe life because we live in a system where long stability occurred, otherwise we wouldn't be here to ask. That's selection bias. Countless galaxies burned hot and quenched early, or never accreted enough cold gas to form rich disks. We inhabit a rare Goldilocks spiral, so we experience regulation. The pattern is real, but our perspective amplifies it and makes it feel more special than statistics alone would predict. 13. Tests the idea must survive. If galaxy as living system is more than poetic framing, it should sharpen predictions. What distinct, measurable behaviors would it imply? For example, A. Tighter than expected regulation of star formation efficiency across wildly different environments. B. Active responses that anticipate rather than merely react. A. High bar. C. Evidence for self-maintained boundaries, membrane analogs, or information-bearing structures that are copied with fidelity into independent systems. In practice, the first is partly true but not exceptional. The second is not supported. The third is absent. The metaphor guides intuition, but it doesn't yet yield discriminants that separate galaxies from other self-organized, non-living flows. Number 14. Autopoiesis. Does the galaxy make itself? A classic criterion for life is autopoiesis, a system continuously producing and regenerating the components that constitute it. Through networks of processes it also sustains. Galaxies regenerate stars and gas cycles, yes, but they do not produce the rules that make disks and bars possible. Those come from gravity and microphysics outside the system's control, nor do they manufacture their own boundary conditions. Cosmological inflow and environment are imposed. They remake contents under fixed laws, not the law-generating machinery that living chemistry creates for itself. 15. Why the metaphor still matters carefully used. None of this means the language of life is useless. As a teaching tool, it spotlights the right networks, feedback, cycles, and memory. As a research mindset, it encourages us to look for self-maintaining configurations and to ask how robust they are to disturbance. But clarity demands that we keep the hierarchy straight. Galaxies are ecosystem-like in their flows and equilibria, organism-like in their large-scale coherence. Yet, not alive by strict criteria, no boundary with selective transport, no genotype-phenotype logic, no true reproduction, no agency. The risk is not merely semantic. It can misdirect explanation. We should be impressed by what physics alone can build without importing teleology. 16. a better framing. So, what should we say? Try this. The Milky Way is a self-organizing, far from equilibrium astrophysical ecosystem. It sustains star formation for billions of years via nested feedback loops. It recycles matter across disk and halo. It stores a history in orbits and chemistry, and it drifts through recognizable developmental stages. Those claims are strong, precise, and testable. No biology required. They honor the galaxy's grandeur without diluting what makes life unique. If the word alive remains irresistible, we can domesticate it. Alive as a metaphor, not a fact useful to evoke persistence, misleading when pressed into proof. The cosmos is generous with patterns. Some patterns think, most don't. The Milky Way's achievement is to be a pattern so stable and so fecund that thinking became possible inside it. That's miracle enough without stealing a word that belongs, for now, to cells, forests, and worlds that remake themselves by code. Let's take the metaphor out for a walk, not to prove the galaxy is alive, but to map its physics onto a body our intuition understands. Organs are coordinated machines, each with a job, all linked by signals and flows. If the Milky Way had organs, where would they be? How would they talk? And what would break when one overpowered the rest? The point isn't cuteness, it's clarity. A good organ map turns abstract dynamics into narrative causality. A heart that sets rhythm, lungs that exchange, vessels that distribute, a skeleton that holds posture, and tissues that adapt or fail under stress. With that lens, the galaxy's complexity becomes legible. A living heart squeezes and relaxes. The Milky Way's pacemaker runs on 2 clocks. The fast beat is clustered star formation, local surges that ignite, blow, and fade within a few million years, each burst hurling radiation, winds, and supernova shocks into surrounding gas. The slow beat is the core. Our supermassive black hole, usually quiet, occasionally erupting. When gas strays inward, an episode flickers on. Jets or wide winds inflate vast lobes above and below the plane. A systole that stiffens the halo and retunes conditions for tens of millions of years. Between these beats, the disk rests in diastole. Clouds gather, cool, and prepare the next contraction. Breath is exchange. Oxygen in, carbon dioxide out. The galaxy breathes through galactic fountains. Supernovae punch hot chimneys. Gas rises into the lower halo, cools, mixes, and falls again, spiced with metals. That's inhale and exhale bound into one arc. Over stronger episodes, central starbursts or black hole flickers, the galaxy coughs harder, venting winds that reach deep into the circumgalactic medium. The analogy isn't perfect. Galaxies don't need oxygen, but they do need exchange. Remove the breath, and the disk chokes on its own heat and momentum. Make it too violent, and the chest empties. Star formation starves. Healthy lungs are measured by return. How much of what leaves comes back cool enough and enriched enough to feed the next round? Blood vessels are roots. Pressure is motive force. In the Milky Way, magnetic fields are the vessels and cosmic rays help push. Fields thread the disk and halo, guiding charged particles over grand distances. Those particles, accelerated in supernova shocks, apply a persistent pressure that can lift gas from the midplane and spread energy where gravity alone wouldn't take it. Radiation pressure on dust adds another shove, especially in dense, bright regions. Turbulence finishes the job. cascading energy from large eddies to small. The circulation is not a single loop, but a web of capillaries, arm ridges, bar lanes, supershell rims, and halo filaments. When circulation thrives, no small patch bears the whole burden. When it falters, pockets overheat or collapse like tissue that blood cannot reach. Bones hold shape, muscles impose motion. The dark matter halo is the skeleton, mostly invisible, immensely strong, setting disc posture and well depth. The bar and spiral arms are the muscular system, self-organized patterns that grip mass and do work on it. The bar torques gas inward along straight, shocked lanes and flings angular momentum outward. The arms shear clouds into ridges where compression turns on starbirth. Muscles act by rhythm, not command. So do these patterns. They rotate with their pattern speeds and translate rotation into useful work, moving matter to where it transforms, not letting it slump where it cannot. Even the galaxy's warp at the edges betrays how bones feel external pulls. Posture records both injuries and current tugs. Bodies need membranes. Galaxies are porous, but they do have interfaces. The disk halo boundary acts like a functional skin, a region where density and temperature flip, where fountains break and return, where magnetic topology changes. It doesn't seal, but it selects. The hottest, fastest gas pierces through. Warmer, slower flows, stall and recirculate. Deeper in, the bar and inner ring behave like a digestive tract. Inflows along dust lanes are the esophagus. Shocks near the ring are the acid bath that breaks clouds into digestible pieces. Molecular zones are intestines, extracting usable nutrients. Cold, shielded gas, and passing the rest along. Too much acid and you vent the calories. Too little and you clog the works with unprocessed clumps. Detox and balance, that's the liver's and kidneys' job. The circumgalactic medium, CGM, does both. It stores heat and metals expelled by the disk, dilutes extremes in a vast reservoir, and filters them back via condensation along filaments and clouds. Too much energy injected too quickly and the liver runs hot, keeping gas buoyant and scarce at the disk. Too little, and the CGM radiates, cools, and rains more than the disk can regulate, risking an overeager starburst. The key is mixing time. How long ejected material takes to lose heat, gain mass from entrainment, and descend. That clock tends to hundreds of millions of years, keeps filtration in harmony with the heartbeats below, and sets the flavor of the next meal. Bodies coordinate with hormones' slow, global messages. The galaxy's hormones are light, winds, and rates. The integrated starlight field warms and presses on dust, even far from clusters. The cosmic ray background whispers pressure into diffuse gas. The rate of supernovae sets baseline turbulence for entire quadrants. Even pattern speed plays messenger. A slowing bar sweeps resonances outward, retuning where rings and lanes form across the disk. None of these signals know they're signals, but they bind distant parts into a common mood. When the inner ring bursts, the outer arms feel it later in softened gradients and altered inflow. Real nerves sense and decide. The galaxy's nervous system does neither. Still, resonances act like wires that carry influence. Where a star's or cloud's natural oscillations match a pattern's rhythm, small shoves add coherently. That's how orbits migrate without heating, and how rings appear where lanes cross. It's also how waves travel. Bending modes roll across the disk. Spiral density waves couple bar and arms. Even the halo transmits a shove when a satellite passes. Think of it as coordination without cognition, information-free, signals that nonetheless structure the response everywhere they go. A kick in the outskirts can ring the midplane near the Sun 100 million years later. An immune system identifies threats and deploys targeted counters. The Milky Way has no such agency, but it responds. A merger thickens the disk. Shear and turbulence rise. Collapse slows. A starburst opens chimneys. Outflows vent heat and momentum. The disk cools back toward cloud-friendly conditions. A passing satellite raises vertical waves. Over time, phase mixing and dissipation quiet the ringing. These aren't antibodies. They're physical damping, but they confer resilience. The same nested feedbacks that keep the galaxy steady during quiet years double as convalescence pathways when it's slammed. The cost is scars, warps, flares, and streams that become part of the body plan. Strictly speaking, the Milky Way doesn't reproduce. Yet in our organ map we can still point at reproductive functions. Tidal tails that condense into dwarf galaxies are buds rare, but real. Star clusters are offspring-like packets. Bounded, coherent, carrying the parent's chemistry forward. Most potent of all are protoplanetary disks nurseries, where the galaxy's raw materials assemble into worlds. Those worlds are seeds of biospheres. Meanwhile, the bar plus arm operating system is a copyable plan. When fresh gas arrives, the same anatomy reappears and does the same work. Generation after generation. No genes, no womb. Yet the functions that make more structure are undeniably there. If a physician ran a checkup, what vitals would they track? Star formation rate as pulse. Too fast for too long implies feverish starburst. Too slow suggests impending quiescence. Mid-plane pressure and tumor Q as blood pressure. Too low hemorrhages into collapse. Too high sterilizes cloud formation. Gas fraction as hydration. Metallicity and dust to gas as hematocrit thickening the fluid, aiding cooling but raising radiation coupling. Outflow speed and mass loading as respiratory rate. Exhale strength and frequency. Pattern speeds as endocrine titers. A drifting bar signals maturity. CGM temperature profile as liver enzymes. Are we filtering or failing? Most importantly, the vitals are coupled. Raise gas fraction and pressure rises. Lower Q triggers clouds. Clouds produce feedback that raises pressure back. Pathologies. When an organ dominates, bodies get sick when one organ overwhelms the rest. So does the galaxy. An overmuscled bar can starve the center by driving gas inward until winds launch, leaving a desert behind. Overactive lungs, winds too strong, strip the disk of its future. A feverish heart runaway central feeding heats the halo so thoroughly that condensation halts for ages. On the flip side, weak vasculature fields too tangled to carry pressure. Cosmic rays too leaky lets feedback stay local, inviting cluster-scale blowouts and global instability. Pathology is imbalance, and balance is the poem the Milky Way writes across organs. We don't just dream this map, we observe it in layers. Radio and millimeter lines trace the cold intestines, molecular clouds and bar lanes, while H-alpha and UV highlight beating clusters. X-rays and gamma rays reveal lungs and vessels, hot chimneys, halo lobes, and the glow of cosmic rays. Infrared shows the endocrine haze of dust-borne starlight soaking the disk. Stellar kinematics from precision astrometry chart the skeleton's sway and the nervous system's resonant wiring. Wavelength family is a diagnostic MRI. Ultrasound. Blood panels stacked to recover anatomy we cannot cut into. With patient, multi-band imaging, the metaphor stops being whimsy and starts becoming a systems diagram. The usefulness of the map is causal. A bar episode is not just a shape. It's a shift in muscular work that will alter endocrine rates, lung strength, and liver filtration. An apparent wind, strong winds clearing a starburst, comes with a bill. A hot halo that won't rain for a while. Inflow without digestion is as useless as calories without enzymes. Digestion without vasculature leaves resources stranded. Vasculature without a heart becomes aimless drift. The Milky Way's resilience lives in redundancy. Many pathways to spread energy, many timescales to damp swings, many organs able to borrow slack from neighbors when one stumbles. No metaphor survives pressure forever. There is no true skin. There are no neurons. The heart doesn't choose. The galaxy is a self-organized flow, not an organism with goals. Yet the organ map sharpens instinct and storyboard. It lets us storyboard a collision as injury, skeletal torque, triage, immune-like damping, fever, pulse racing, cough, winds, convalescence, liver cooling, and return to work, muscles resuming traffic. It suggests visuals that carry science. Heartbeat pulses blooming over the poles, breath rising in fountains, vascular filaments lit by cosmic ray glow, a liver-like halo shading from hot to cool as metals mix. Use the map to tell causality, then set it down when it tempts teleology. Seen this way, the Milky Way doesn't become alive. It becomes legible as a coordinated, far from equilibrium ecosystem with organ-like subsystems. The heart sets tempo. Lungs exchange. Vessels distribute. Bones and muscles govern posture and work. Liver and kidneys filter. Endocrine signals synchronize. Resonant wiring coordinates without cognition. Immune-like damping grants. Resilience. Reproductive functions bud, seed, and copy a plan. That ensemble makes continuity under change a definition-adjacent property we associate with life. The miracle is not agency. It's reliable cooperation among blind processes, producing a body plan that keeps reappearing as fresh material arrives. Stand outside on a cold, transparent night and try a simple exercise. Pretend the Milky Way is not a backdrop, but a process, a slow, resilient flow that makes and remakes itself. Then ask, if that's true, what does it mean about us? We've argued that the galaxy regulates, metabolizes, remembers, grows, and even reproduces in loose ways. We've also admitted all the reasons that alive is a stretch. The reflection begins in that tension. What do we gain, and what do we risk by seeing the Milky Way through the lens of life? Definitions are fences. Life on one side, non-life on the other. But when you stare at galaxies, climates, forests, and cells long enough, the fence looks less like a wall and more like a slope. At the top are organisms with membranes, codes, and agency. Below are systems that never get there and yet act lifelike. They stabilize, circulate, and persist. Seeing a slope doesn't erase the difference between a cell and a spiral galaxy. It does something subtler. It asks us to track functions and degrees. How tightly does a system regulate itself? How richly does it store and copy information? How closed is its boundary? How strongly do its flows regenerate the very patterns that make the flows possible? By those questions, a forest sits closer to a cell than a dune does. A galaxy sits closer to a forest than a flame does. The Milky Way is far down the slope compared to you, but it's on the slope. Why does that matter? Because where we draw borders shapes how we look for meaning. If life is only chemistry in a membrane, then galaxies are scenery. If life is also the broader project of persistence under change, then galaxies are contexts that make local life more likely machines that generate habitable time. When we think about survival, we think about food, water, shelter. The galaxy thinks about none of that because it doesn't think, but its flows produce something those needs can't exist without: time. Time to build heavy elements over billions of years. Time to recycle them through clouds until cooling becomes easy. Time to form stars with gentle, long-lived output. Time to let disks around those stars coagulate pebbles into planets and atmospheres. Time to let chemistry try, fail, and try again. The steady heartbeat of regulated star formation isn't a moral triumph. It's a physical habit. But from the inside, for worlds like ours, it feels like grace. A long, stable lane in which fragile experiments like minds can run. If you press the metaphor just until it creaks, but not until it breaks, you could say the Milky Way's lifelike mission is to buy time. To maintain a state that keeps gradients flowing and keeps renewal possible. That's what metabolism does in a body. It's what climate does for a planet. It's what a spiral disk does for its stars and worlds. The galaxy is a time-making engine. A trap hides here. If the Milky Way makes time for worlds, then maybe worlds are the point. Maybe a galaxy wants to seed biospheres. No, that smuggles purpose in where there is none. The flows we've described have no goal except the one physics allows. Continue if you can. And yet meaning leaks in at the edges, because we bring it. Meaning is not something a galaxy emits like light. It's something observers extract like heat from a gradient. Here is a cleaner way to put it. The Milky Way's structure is fertile. It cultivates conditions under which meaning-making creatures can arise. Fertility is not intention, it is consequence. The galaxy makes many things: bars, arms, rings, fountains, halos, and among them it makes opportunities. Some are seized by chemistry and evolution, some aren't. To live in a fertile system is to be a beneficiary of luck with a physical address. That address changes how we think about ourselves. We are not visitors in a dead museum. We are late products of an ongoing flow. The iron in our blood is bookkeeping in the galaxy's metabolism. The water in our cells is condensed breath from its fountains. The warmth we stand under is starlight, paid for by regulated collapse. Even if the Milky Way has no intentions, it is fair to say we belong to it. Shift perspectives and three emotions arrive in sequence. Humility. If the galaxy is a self-maintaining ecosystem and we are children of its long patience, then our accomplishments are not from scratch. We inherit a working platform, a stable main sequence star, a quiet thin disk neighborhood, an era with modest merger rates. Every tool we make, from radio dishes to fusion dreams, is a local modulation of the galaxy's energy flows. The right response to that inheritance is gratitude, not conquest. Awe. The Milky Way's trick is not raw power. It's cooperation among dumb parts to yield smart outcomes. Gravity tries to clump, feedback tries to puff, rotation tries to shear, magnetic fields try to guide, cosmic rays try to push, cooling tries to condense. No part knows anything. Together they yield steadiness. Awe is what we feel when mindless rules produce structures so reliable that minds can lean on them. Dread. All self-maintaining systems have failure modes. Lungs can cough too hard, hearts can race, skeletons can crack. Galaxies, too, can starve if inflow dwindles. They can overheat halos with prolonged outflows. They can be jolted by mergers. On human timescales, the Milky Way is a rock. On galactic timescales, it is a wave. Dread enters not because catastrophe is near, our local era is calm, but because the continuity we depend on is contingent. The long lane was won. It can, someday, be lost. Hold all three emotions at once, and you get the right stance: smallness, wonder, and urgency. If the galaxy is not alive but behaves like an ecosystem, how should beings inside it behave? Not because the galaxy cares, because we do. A first principle: do not shorten the lane. Civilization is excellent at making fast gradients. Burn something now. Harvest a surplus now. Spend stored structure now. If our future technologies merely accelerate local dissipation without adding regenerative capacity, we risk narrowing the window we inherited. By contrast, a civilization that learns to surf the Milky Way's flows using steady starlight, tapping long-lived isotopes, recycling materials as ruthlessly as the galactic fountain does, acts like a good resident of a self-maintaining system. The metaphor is not a law, it is a nudge. Build like the galaxy, feedback first, recycle forward. A second principle: export entropy wisely. All persistence requires exporting disorder. The galaxy does it with light and winds. We do it with heat, waste, and radiation. The question is not whether to export, it's where and how. Aim your waste streams where the larger system can absorb them with minimal damage to the structures we care about. Biospheres, climates, niches. The galaxy's example is blunt. Hot gas belongs in the halo, not trapped in the disk. Analogously, long-lived pollutants belong nowhere near oceans and soils. The ethic is match waste to buffers, not to cradles. A third principle: keep options open. The Milky Way's resilience comes from redundancy, many channels to move energy, many timescales to damp swings. Societies can mimic that. Diversify energy sources, diversify knowledge, diversify habitats, from cities to off-world stations, someday. Options are a moral good because they preserve choice when disturbances come. The galaxy writes this lesson in rings and arms. When one lane clogs, another still flows. What about everyone else? If galaxies are fertile, where are all the listeners? All the lights? All the voices? The Fermi question haunts us because it ties our local story to a cosmic one. A galaxy that produces many worlds and much time should fill with civilizations, unless something prunes the tree. There are friendly answers. Maybe technical life is rare. Maybe it is shy. Maybe it is transient but reappears often enough that at any given moment, the disk holds only a handful of sparks. There are harsh answers. Maybe steady star formation is necessary but not sufficient. Maybe you also need gentle giant planets, late heavy bombardments, plate tectonics, a magnetic field, benign neighbors, lucky timing across dozens of axes. The Milky Way could be fertile and still host very few minds. If that's so, then the implication flips from comfort to responsibility. It means that a galaxy's fertility is not a guarantee but an invitation, and that invitations can be wasted. For us, that raises a blunt, uncomfortable meaning. Maybe we are not merely products of the Milky Way's time-making engine. Maybe we are custodians of it in one locale, charged by no one but ourselves to keep the experiment going. The Milky Way's calendar prints headlines we will never see but can still understand. Spiral patterns will evolve. The bar will slow. The sun will drift. New clusters will flare and fade. Far ahead, the galaxy will meet Andromeda. Over billions of years, the two disks will tangle, fling streams, scramble orbits, and settle into a new body plan, a giant, more spheroidal Milkdromeda. Star formation will surge for a time, then likely quiet, as gas is heated and consumed. There is no tragedy there, only change. The ecosystem will write a new chapter with the same old rules: inflow, feedback, memory, growth, restraint. Does that cosmic future erase our meanings now, or does it add to them? Knowing that galaxies merge and patterns drift is not cause for nihilism. It's context for urgency. Meaning is not permanent because nothing is. It is made, then kept, then passed. The galaxy shows how. Copy the functions that keep you going. Let go of the details that do not. Reform patterns after shocks. Accept that identity is not sameness, but continuity under revision. Let the camera climb. First, it floats above a city where people are looking through telescopes, then above the continent, then the blue planet, then the sun wrapped in a thistle of dust, then the spiral arm, then the bar's traffic, then the halo's faint glow. The Milky Way turns, not quickly, but with posture. Inflows thread, fountains lift, rings shine and fade. Nothing in that view knows anything. Yet the picture is full of relationships. Every feature's fate depends on every other's. If you cut the arm, clouds would starve. If you silence the supernovae, the disk would suffocate. If you overheat the halo, rain would stop. That mesh of dependence is a form of order we recognize because our own bodies run on the same principle. Now let the camera fall back in and stop at a window where someone is awake at 2 a.m., feeling small and lucky. What the wide shot couldn't show is what the close shot can. Value. Value is local and felt love between people. Care for a child. The pull of a song. The dignity of a promise kept. None of that is written in the laws of gravity. All of it depends on a stable lane of time provided by a star, which depends on a lane provided by a galaxy. The cosmic and the human are therefore not rivals. They are nested. To protect the small is to honor the large. We need words that let us talk across scales without lying. Alive is tempting because it compresses 100 functional truths into one syllable. Use it, but mark it as metaphor. Then add a vocabulary precise enough to build on. Self-regulation, nested feedbacks that damp swings, metabolism, flows that transform inflow into structure and export entropy. Memory, patterns that store the past and shape the next step. Development, recognizable stages that reconfigure, not just accumulate. Resilience, the ability to fail without collapse and to reform after shocks. Fertility, the capacity to produce opportunities for complexity elsewhere. Call the Milky Way a self-organizing astrophysical ecosystem with high fertility. That sentence is less poetic, more useful, and no less awe-inspiring once you know what the words mean. In the end, the galaxy story is a mirror. We looked at the Milky Way to learn what it is and discovered much of what we saw was also about us. We thrive when we regulate our appetites, recycle our wastes, and keep our boundaries permeable but protective. We last when we remember, when we store what works in structures that outlive individuals. We grow best when we accept that identity is a pattern that can survive the loss and replacement of parts. We reproduce most meaningfully when we seed worlds, ideas, institutions, children that carry forward the functions we've found worth keeping. These are not galaxy morals, they are human ones. Drawn from a galactic example, a system can be mindless and still be a teacher. Return to the question, what if the Milky Way galaxy is alive? The safe answer is no, not by the strict rules. The interesting answer is that it behaves enough like a living thing that the language of life carefully used helps us see it. The deep answer is that calling it alive is a way of asking whether continuity under change is the heart of life, and whether that heart can beat in things without minds. If it can, then we are not a freak spark in a dead ocean. We are a late stanza in a long song of pattern that the universe keeps discovering. Cells in ponds, forests on continents, climates in atmospheres, and spirals in disks, each making time for the next verse. So stand under the stars and repeat the question softly, not to extract a verdict, but to keep your curiosity honest. If a galaxy can look alive without being alive, what does that make us life inside a metaphor, or a metaphor that learned to live? The Milky Way will not answer. It will continue, which is answer enough.